Nuclear reactions produce energy as the result of the decay of a nucleus. Here to the right we find a decay chain, or the series of steps by which a radioactive element ultimately becomes stable. In this particular decay chain, we see uranium-238, indicated in the upper right-hand corner, undergo decay ultimately to lead-205. The first decay of uranium is alpha emission, as we see a change in the mass number. And as uranium changes to thorium, we lose a helium nucleus in terms of mass. From thorium, however, we undergo two beta decays back to uranium-235. Notice that in this beta decay, the mass number remains constant. After all, it's only alpha emission which results in the change of mass of a nucleus. Every time we undergo one of these transformations, though, we have a peculiar thing happen. For example, when uranium-238 decays into thorium-234 and an alpha particle, we would expect the sum of the masses involved to be equal. That is, we expect the law of conservation of mass to be obeyed. And yet, when we actually measure the mass of uranium-238 and compare it to the mass of the beta particle in thorium-234, what we find is we have a little bit of mass missing. So for 1 mole of uranium-238, we lose about 4.6 milligrams. Where did this energy or mass go? Well, the answer is this mass was actually converted into energy. The missing mass is known as a mass defect, and this mass defect is responsible for the binding energy which holds the nucleus together. How much energy is that? Well, we can relate the mass defect and the energy through Einstein's equation, E equals mc squared, where E is the mass in kilograms, and the speed of light, which is rounded, we use 3 times 10 to the 8th meters per second squared. We find that we have a tremendous amount of energy available from the transformation of 1 mole of uranium. This far outstrips any chemical reaction. In fact, the benefits of nuclear reactions outweighs fossil fuels considerably. One of the reasons why we never went completely nuclear was because of the fossil fuel industry. The benefit of this is that we have no greenhouse gases, which is quite nice given our current climate change predictions. And if we went all nuclear, we could still have an energy abundance and surplus without the greenhouse gas if we could move to things like electric cars and motors. The problem we've always had, though, is the potential for radiation leaks and disasters and causing environmental issues. We'll steer away from that for now and get back to talking about the actual energy. So what we find is that the missing mass has actually been transformed into energy, and the missing mass we described as being the mass defect. The mass, as it's changed into energy, is called the binding energy. The binding energy is how much energy is actually being used to hold the nucleus together. So what we find as we increase the total mass of the element, for example, going from helium to iron to uranium, the binding energy constantly increases. It takes more energy to hold bigger nuclei together. Yet if we look at the nuclear binding energy per nucleon, which is simply the total number of protons and neutrons that any given isotope has, we actually find that it doesn't change much. It does change, don't get me wrong, and there are some important consequences of it. But if we look at the nuclear binding energy per nucleon for all the elements on the periodic table, what we find is that we have a maximum binding energy, or a most stable nucleus. And that nucleus is iron-56. If you go back and recall from the introduction about the first generation of stars, you'll remember that iron was where the stars stopped forming new elements at. We didn't have any new elements after iron in the first generation of star. There just wasn't enough energy to continue putting more protons and neutrons together. All elements seek to have a nuclear binding energy of iron. That's where they want to be. That's where they're most stable. And the way they get there is through a process either known as fission, which is nuclear decay, or fusion, which involves bringing two atoms together to form a new one. Nuclear fission is currently possible and self-sustaining. We have nuclear power plants after all. And we're working to achieve nuclear fusion on a self-sustaining level. We can do nuclear fusion, but we can't make it self-sustaining. And one of the things we'd like to be able to do is have hydrogen undergo nuclear fusion, because you see hydrogen is at the lowest spot on the left-hand side there. And to go up to helium-4, we have an incredible amount of energy being produced from just making helium. And the nice thing about that is there's no radiation associated with it. It's just one big exothermic reaction. So this is one of the holy grails for energy solutions, is being able to undergo hydrogen fusion and move away from fission reactions and fossil fuel type plants. While we wait for that day in which nuclear fusion becomes possible and self-sustaining, we can still use nuclear fission. In a nuclear reactor, we use uranium at We use uranium-235 as a fuel source in nuclear reactors because it readily undergoes fission. The result is we have to constantly monitor our nuclear reactors to make sure they don't achieve something known as supercritical mass. Normally, uranium's at subcritical mass. That is, that the rate of radioactive decay is such that the reaction remains non-self-sustaining. One of the results of taking uranium-235 and allowing it to decompose is it produces 2 new neutrons for every uranium that decays. Well, those 2 neutrons could go and hit 2 uranium-35 atoms, resulting in 2 more neutrons, but with subcritical mass, they often don't find another uranium atom. They find a different element. In a nuclear reactor, though, we can take the uranium and enrich it and then put it in the presence of other uranium atoms to get to critical mass. Therefore, this reaction is constantly sustaining, and it's producing 1 neutron for every, it's producing 2 neutrons for every uranium that's undergoing decay, but only one of those neutrons is actually finding another uranium atom. So we say that the rate of neutron loss is equal to the rate of neutron creation. And the reaction is self-sustaining at that point, and that's where we try and keep our nuclear reactors at. If things go bad, though, we get to supercritical mass, where the rate of neutron loss is less than the rate of neutron creation, meaning we're constantly creating more and more neutrons, which are finding other atoms to undergo fusion with, and things can get very out of control quickly. In a nuclear reactor, we play with this reaction all the time. We have our uranium in little pellets, and we stack those pellets in to create rods. And then what we do to prevent reaching a supercritical point is we lower control rods to help moderate the reaction. Basically, a nuclear reactor is one big steam generator. If we look at area 1, we have a pressurized water system which is in contact with the core reactor, and so the result is this water heats up. Well, the water is also pumped into an area where we undergo heat exchange, and that heat is exchanged into a separate canister, or well, if you will, and heated up to the point where it creates steam. The steam pushes a turbine, and as the water or the steam loses energy, it condenses back down into water and is pumped back to the heat exchange. Finally, to help facilitate the condensing of water after the steam has gone through the turbine, we have a coolant pump, which takes outside water and just pumps it around so that the steam comes into contact with cool water to help it condense. Within the reactor itself, we have control rods. Control rods help prevent reaching supercritical mass, and they can be throttled to increase or decrease the energy output of the reactor. It doesn't change the rate of decay, it simply helps prevent energy being released by having other atoms absorb the neutrons that are the result of the decomposition of the uranium. So if we need more energy, we lift the control rods up. If we need less energy, we put it down. And that controls the heat that the water is absorbing. Now, one thing that we've done in the United States that's very clever is we built our control rods such that they are vertical, so that in the event of a power loss or something going wrong, there's a pin you can pull and all of the control rods will drop down between the fuel rods and avoid any sort of supercritical mass being achieved. Not all nuclear reactors were built this way, and as a result, there has been several nuclear, I won't say disasters, but environmental disasters as the result of this carelessness. Earlier I said nuclear fusion is the energy source of the future, and it really is. The amount of energy that can be released by simply taking some hydrogen atoms and smashing them together to produce helium is quite remarkable. In fact, we're currently building a reactor in France that we believe will be self-sustaining as part of a joint task force among several countries to make sure that this is a possible achievement to do. Currently, we're slated to see the reactor go online in 2025, and hopefully that will be a huge, huge success, and so we can begin to modify the nature of our energy consumption in the United States.